All right, we're back recording. All right, we're getting towards the end of class. So FRQ, I gave you guys this FRQ page has this FRQ on one side and this separate FRQ on the other side. They're each 10 points. Now, I do want to put these scoring rubrics in your hands so that you can go through and see exactly what an AP grader would see. So you can think like an AP grader. Just one because I think that's all you have a good time scoring class, right? But here, I do want to give you guys a quick rundown about how to think about these. Okay, just big picture. Okay. Right, so this one, you have this pulley and there's a string wrapped around. You pull up some F sub S. Now, guys, S in this case stands for string, like force and string. So there's a string force, maybe like a tension force. Okay. And one of the questions they asked is derive the expression for tangential acceleration. And that's after you make the free body diagram. Okay, so here's the free body diagram they came up with. There's the weight of the pulley, F sub G for gravitational force, the force from the string at the edge. Okay. And then there's the force from the axle going up. Hey guys, what's the sum of those forces? Yeah, well, if it's not, they should roughly, yeah. Actually, it might be zero because this thing's not moving up or down, right? It's not translating up or down. The axle is fixed in place. Okay, but after that, can you come up with the angular acceleration? And how about this? They say use Newton's second law in rotational form. Guys, what's the regular version of Newton's second law? F equals ma. Some version of that. Okay. Now, guys, what's the rotational equivalent of that? Tau equals I alpha. Aha. Right. And torque is R cross F. So you could do R cross F equals I alpha. Can you do that?
Yeah, we did.
Okay.
Could you have it mixed up?
How's that?
I forget. Is it alpha equals
Yeah, you can do that. Yeah, guys, you can totally do A equals F, or actually, I prefer to normally write like this myself. Anyway, okay. Yeah, you could do the resulting angular acceleration as the torque acting on the rotation. Yeah, you can totally do that. Yeah. Right, since I got the start here, we'll continue here. Right, so R could be the radius of the pulley. So R, this is the string force. So F sub S. Now they did tell you the rotational inertia of this pulley. It was something weird. Somehow they got 1/3 mr squared, so it's not a uniform disk because then it would have been half mr squared. So somehow it's 1/3 mr squared. So just go ahead and take their given value, plug that in. Okay. Hey guys, since they wanted the tangential acceleration and they underlie tangential, they don't actually want alpha. They actually want A, don't they? So guys, what is alpha in terms of A? A over R, isn't that true? So that would sub in for that alpha right here. Is that true? Okay. Now, at this point, could you guys do a little algebra, maybe cancel some stuff, shuffle some stuff around and solve for that A? Okay. This basically leading you towards the answer. Okay. But there was a second part, which is they say, what if? All right, you guys ready for this? Because I want to see if you guys got this. Okay. What if you replace the string tension with a block of equal weight? Right? So, for example, before you were pulling with a tension, I'm going to make up something. Suppose you were pulling with 10 newtons. Can you guys see that? I'm pulling with 10 newtons. Okay. But I get rid of that pulling force. Instead, I replace it with a block that weighs 10 newtons. Okay? Right. So, guys, are those two situations identical? Yes or no? No. Which one accelerates faster? Huh. Show hands. Show hands. How many of you think the first scenario would accelerate faster?
No,
They're not equal. How many of you think the second situation accelerates faster? Okay. I would have said the first situation, and I'll tell you guys why. Okay. Because if this block weighs 10 newtons and it's accelerating down, isn't that like an accelerating elevator?
yeah.
So if you look at a free body diagram on the block itself, which force is bigger, the down force or the up force? The down force, because it's accelerating down. So if it weighs 10 newtons, it might be 10 newtons down, it might only be like 9 newtons upwards, for example, right? Oh, now the string tension is only 9 newtons. So now from the point of view of the pulley, it's not being pulled as hard. You guys see that? So it's not going to accelerate as much. Okay. Now they go through exactly how to score this. Now again, I want to put this in your hands pretty soon. But before we do, let's flip over and look at this other one. Okay, so here we got the start going to this bar around this axle. It's going to start spinning. Super. Okay. And they want to find what's the they look for a linear velocity. But I would go through angular motion, find angular velocity first. Okay. But you guys told me this is conservation of angular momentum, and they kind of direct you that way anyway. So let's do sum of, oh yeah, angular momentum initial equals sum of angular momentum final. Okay. You guys, anytime you see this, because you're going to see the situation somewhere on the AP exam. It might be the FRQ, it might be the multiple choice questions. It might be turned this way. The quiz version, I gave you guys a paddle wheel. It's all the same thing. Okay. So there's a collision and it's rotating. That's conservation of angular momentum. Okay. Guys, what's the angular momentum of a dart moving in a straight line? Mass of the dart times velocity of the dart, that's radial momentum, times this radial distance r. You guys see this little r right here? So MVR. That's the source of all the angular momentum. Okay. But another way to express angular momentum is what times what? Yeah, I times omega. Right? Isn't that true? L equals I omega. Okay. And then if you're in class, you guys see that those ice skaters over there. L equals I omega. Is it? Okay. Now, guys, when this dart is stuck in this bar and the whole thing's rotating together, there's the eye of the bar. I'll call it I sub bar. Plus, there's also the dart has a little bit of inertia itself too, doesn't it? It's a mass at this location. Guys, what's the rotational inertia of a point mass? Guys, rotational inertia of a point mass. What is it? mr squared. You guys remember that? Okay. This is mass of the dart. This is mass of the dart. Okay. And then this would be times omega final. Okay. Okay. Now, guys, if you want to solve for v, like a linear velocity, what is omega equal to? V over r. Right. So we got. Okay, so I think that would set you on the right path there. Right. Here's a diagram they had during that collision. Right. Okay, let me get these scoring rubrics in your hands, and again, I want you guys to really go down and think like an AP grader and see point for point, right, how you would score something like that.